Assalamu alaikum. As there was a technical glitch this morning that I could not record the lecture, so I'm trying to record it offline, and I apologize again for the technical issue that happened this morning. So as a quick review for the last lecture, we started talking about the pure Aloha protocol. And as we discussed in today's class, that we start the transmission of one single frame by setting the k value to 0, and then we send the frame and we wait for the acknowledgement, which indicates that whether or not we have a collision. So if the acknowledgement has been received, so we reach the success stage. Otherwise, we increment the k value by 1, and we perform the back-off procedure. As we said, that the back-off procedure here is performed by generating a random number. So each node will generate a random number which is in the range of from 0 all the way to 2 to the power k minus 1. So assuming that k is 2, so 2 to the k to the power k is 4. So the range of values for k is from 0 all the way to 3. So 0, 1, 2, and 3. So each node will perform a random number generation, and will calculate a random number from 0 to 3, and depending on this number, the node will have to wait for a time which is multiples of k. The calculation of k, as this example explains, so first we calculate the propagation time. The propagation time here is calculates the time that the signal arrives, or the signal transmits from the beginning all the way to the end of the cable, and then each node will independently generate a random number using the k parameter and calculates the range of numbers. So for example, if k is 1, the range will be 0 and 1. So each node will generate a random number, whether 0 or 1, and depending on that, the node will, so assuming that if we have the propagation time is 2 milliseconds, so the node will either wait for 0 millisecond or 2 milliseconds. So each node will generate a random number. If the random number is 0, then the node will transmit right away. If the random number is 1, then the node will wait for 2 milliseconds. K is equal to 2, then the range will become 0, 1, 2, and 3. So each node will generate a random number within this range. If the random number is 0, then the node will not wait for any time, and it will start transmitting right away. If the random number is 1, then the node will have to wait for 1 propagation time. If the number generated is 2, then the node will have to wait for double the propagation time, and so on. So when k is equal to 3, the range becomes a 0, 1, 2, all the way to 7, which is 2 to the power k minus 1. And also we have to be aware of the fact that the maximum value for k is 10. So if k is more than 10, we keep it at 10. So 10, the range becomes from 0 all the way to 1023. From 0 to 1023. So because 2 to the power 10 is 1024. So the vulnerable time is a very important parameter for the pure Aloha network, and to calculate that, we imagine that if we have a node A which is trying to send a frame. So node A is trying to send a frame, and we can assume that the frame size is fixed for all the nodes. So this is the beginning of the frame and this is the end of the frame. So if node A sends at time t, the node will spend a time which is equal to the transmission time, which makes this time a t plus t transmission. So the vulnerable time talks about the time within which I should expect the collision might happen at any point in time. So if any node, assuming node B, tries to send within the time duration t to t minus t transmission, so if a node tries to send at any point in time here within this range, the transmission will start at this point and will overlap with the transmission from A, which means that if this is node B, which means that the transmission from node B will overlap with the transmission for node A, which means that there is a collision. So at any point in time within this range, the node will have collision, and at this point in time there will be collision. The only time that there will be no collision is if the node starts at a time which is above t plus the transmission time, above this time here. So if a node transmits after this time, then the collision will not happen, which means that all this time is a vulnerable time, which means that if any node transmits within this range, the collision will happen. So with that said, the propagation time, the vulnerable time is a very important parameter, which in the case of pure Aloha is double the transmission time. So the vulnerable time is equal to double the transmission time, and that's a very important rule that we need to keep in mind. In a pure Aloha network, we have each node can transmit a frame of a length 200 bits, and the medium is shared, and the medium itself has a bandwidth of 200 kilobits per second. So from those two values, we right away can calculate the transmission time. So any node can spend a time which is this value divided by this value, which calculates the amount of transmission time that any node can spend to send a frame of length 200 bits on a medium which is 200 kilobits per second bandwidth. So what is the requirement to make this frame collision free? Which means that we can calculate the vulnerable time, and the vulnerable time is simply double this transmission time. So the average frame transmission time in that case is 200 bits divided by 200 kilobits, which is 1 millisecond. So 1 millisecond came from the fact that 200 divided by 200 times 10 to the power 3, which is 1 times 10 to the power minus 3, which is 1 millisecond. Okay, so so the vulnerable time in that case is simply double that time, which is 2 milliseconds. So the vulnerable time is very important parameter that we use to calculate what we call the throughput. So the throughput here, so this throughput measures the probability of successfully sending one frame to the receiver without having to wait for retransmission. So the throughput as a function is evaluated based on another parameter, which is g, and g here is a very important parameter, which is defined as the average number of successful transmissions per transmission time. Okay, the average number of transmissions for all the nodes in the network per transmission time, yani within a duration which is the transmission time. So within a duration which is equal to the transmission time, how many transmissions that all the nodes in the network can generate. Assuming that the transmission time is 1 millisecond, so how many nodes send on the average send within 1 millisecond? If the transmission time is 1 nanosecond or 1 microsecond, so how many nodes can on the average send within 1 microsecond, and so on. So this 2, as we can imagine, this 2 here is based on the fact that the vulnerable time is double the transmission time. So this 2 is coming from the double the transmission time. So the throughput is an exponential, is a mix of exponential and linear function based on the parameter g. So we can simply measure or analyze the throughput. So the throughput will simply become a function of g. So as a function of g, when g is 0, the throughput is 0, and it will increase with a mix of exponential and linear time up to a value, which in that case g equal to half, and we'll talk about why it's half. After that, we will reach the maximum throughput. After this, when g is more than half, the system will start to decay, which indicates that after the value of g equal to half, the system will start to decay in terms of throughput. So the throughput will decrease, not increase. And when the value of g is low, the throughput will increase, which makes sense, because when the value of g is low, this means that the load on the network is low, so the probability of collision will be low. So the probability of sending packets successfully without having any collision will be higher. So any transmission that we will do, it will go through. That's why the throughput increases. After the value of g equal to 1/2, the load on the network starts to grow to the extent that we will have more and more collisions. Okay, and the more collisions we will have, the more that the throughput will decay. The throughput will decay against g exponentially as we can see. So to get the value of g that maximizes the throughput, we can simply get the derivative of s with respect to g. So the derivative of s with respect to g equals to, we have two functions, exponential function and linear function. So we assume this is f1 and f2. So the derivative of multiplication of two functions is the derivative of, so we keep the function f1 and we get the derivative of the second function f2, which is in that case minus 2 e to the power minus 2g, plus we get the derivative of the first function g here multiplied by the function f2. So in that case the derivative of g is 1, and the other function is e to the power minus 2g. So this derivative is equal to 0, which means that if we can simply multiply by e to the power 2g, which take this away. So we will have minus 2g plus 1 equals to 0, which means that g is equal to 1 over 2. And S maximum, in that case, the maximum S is simply S max is half e to the power minus 1, which is around 0.184 or 18%, or 18.4%. Okay, so this is the efficiency of the system, or the maximum throughput that we can get from a pure Aloha system. A very simple example. A pure Aloha network that has a frame rate of 200 bits. I think we stopped here, so we can simply stop here and continue next time.